is one of the deepest signatures of reality. It is older than starlight, older than planets, older than chemistry, and older than the quiet architecture of galaxies. Long before the universe became a place of worlds, moons, oceans, nebulae, and black skies, it was a dense and radiant state where matter had no familiar shape. Every atom in every body, every grain of dust, every stone, every living cell descends from a history of cooling. The universe began in a state of overwhelming temperature, then expanded, thinned, and slowly allowed structure to appear. To follow the hottest places in the universe is to follow a ladder. At the lower rungs, heat still feels familiar. There is the sun, the furnace that rules our days, whose surface looks absolute from Earth and whose core quietly powers nearly all life we know. Then come hotter stars, violent stellar atmospheres, magnetic storms, explosions, collision fronts, dead stars, feeding black holes, particle jets, and finally the conditions that existed when the universe itself was young enough to be a single furnace without walls. This is a journey through extremes, arranged like a cosmic ranking. It begins with the fire we live beside, then climbs toward temperatures that break matter apart. At every step, the meaning of heat changes. Sometimes heat is fusion, sometimes it is shock, sometimes it is gravity turning motion into radiation, sometimes it is magnetic energy tearing plasma open. At the highest levels, heat becomes almost philosophical, a measure of how close reality comes to losing every form it has acquired. The strange thing is that the hottest places are often hidden. The sun's surface is bright, yet the core is vastly hotter. A blue star dazzles, yet its deepest interior is harsher than its light. A galaxy cluster may look calm through a telescope while its thin gas burns at tens or hundreds of millions of degrees. A neutron star can be only the size of a city and still contain temperatures and densities beyond ordinary imagination. The universe rarely places its most extreme fire where the human eye expects to find it. So the question is simple, and the answer leads far beyond ordinary fire. What are the hottest places in the universe, and what happens to matter when the temperature keeps rising? The list begins close to home. The first great fire on the list is the surface of the sun. From Earth, it appears as the natural definition of heat, the brilliant center of the sky, the source of daylight, seasons, weather, and life. The visible surface, known as the photosphere, reaches roughly 5,500 degrees Celsius. That number is already severe enough to vaporize many familiar materials and turn metal into liquid. A spacecraft drifting too close without protection would be destroyed long before touching any physical surface, because the sun has no solid ground to stand upon. It is a sphere of plasma, a body made of ionized gas held together by gravity. Yet the photosphere is only the visible skin of a far deeper engine. It is the layer from which most sunlight escapes into space, the layer that gives the sun its apparent edge when viewed from Earth. Through telescopes and solar observatories, this surface becomes textured and restless. It boils with granules the size of countries, each one a column of hot plasma rising from below, cooling slightly, then sinking again. Dark sunspots appear where magnetic fields suppress convection and lower the local surface temperature. Even those darker regions remain hotter than almost anything on Earth. The surface of the sun matters because it is the first threshold in our understanding of cosmic fire. It is bright enough to dominate an entire planetary system, yet it is mild compared with what exists below and beyond it. The human mind often confuses brightness with ultimate temperature. The sun corrects that instinct. What dazzles the eye is only the final layer of a process that began deep inside a gravitational furnace. At this level of heat, atoms are already stripped and broken into plasma. Electrons move freely. Magnetic fields grip and shape the charged material. The surface is turbulent because the sun is constantly moving energy outward from the core. Every second, immense quantities of energy cross through this region and begin their journey into space as sunlight. Some of that light reaches Earth after about 8 minutes. It falls onto oceans, leaves, deserts, cities, skin, and glass. It becomes warmth, wind, weather, and food. There is a simplicity in beginning here. The sun is ordinary by cosmic standards, yet it is the star that made our questions possible. Its surface is not the hottest place in the universe, but it is the hottest place most directly written into human experience. Every hotter entry in this ranking becomes harder to imagine because each one moves farther from the kind of heat our senses evolved to understand. Below the visible surface, the sun becomes a different kind of object. Its core reaches roughly 15 million degrees Celsius. There, pressure and temperature are high enough for nuclear fusion. Hydrogen nuclei move through the dense plasma until, through a chain of reactions, they become helium. A small fraction of mass is converted into energy. That loss of mass is the source of sunlight, the hidden accounting behind every day on Earth. The solar core is not a place of flame in the earthly sense. Fire on Earth is chemistry, the rearrangement of electrons around atoms. The sun's core works at a deeper level. It changes atomic nuclei themselves. Protons must overcome their electric repulsion, which normally keeps them apart. Gravity supplies the pressure. Temperature supplies the motion. Quantum tunneling completes the process, allowing fusion to occur even when classical physics would make it nearly impossible. The sun shines because nature allows particles to pass through barriers they cannot fully climb. Energy born in the core does not immediately escape. Photons scatter through the dense solar interior in a long, tangled migration. A photon may be absorbed and re-emitted countless times before its energy reaches the photosphere. This journey can take thousands of years. The sunlight that reaches Earth in minutes may have begun as energy produced long before human history, long before the modern world, long before the person watching the sky was born. The solar core reveals the second lesson of this ranking. The most important heat may be buried. Nothing in the visible surface gives a direct human impression of 15 million degrees. The core is hidden by hundreds of thousands of kilometers of plasma. We infer it through models, neutrinos, helioseismology, and the measured behavior of the sun. The deepest fire of our star is known through science rather than sight. In cosmic terms, the sun's core is still moderate. It is powerful enough to sustain fusion for billions of years because the sun is balanced and stable. It burns slowly compared with massive stars. That slowness is a gift. If the sun were much more massive, it would be brighter and hotter, but its life would be shorter. Earth's long biological history depends on a star that spends its fuel with restraint. Still, the core is a furnace beyond any natural heat on Earth. It is where gravity becomes light, where pressure becomes time, where hydrogen becomes the future. Everything alive on Earth is, in a practical sense, downstream of this hidden heat. Above the sun's surface, the temperature rises again in a way that seems strange at first glance. The corona, the sun's outer atmosphere, reaches around 1 to several million degrees Celsius, far hotter than the visible photosphere below. During a total eclipse, the corona appears as a pale halo surrounding the blocked solar disk. It looks delicate, almost ghostly. In physical terms, it is a vast region of superheated plasma shaped by magnetic fields. The corona remains one of the most fascinating problems in solar physics. Heat normally spreads outward from a source and weakens with distance. Around the sun, the outer atmosphere somehow becomes much hotter than the visible surface. Magnetic fields are central to the explanation. They rise through the solar plasma, twist, reconnect, and release stored energy. Waves may also carry energy upward and dissipate it in the corona. The full mechanism is still studied, and missions such as Parker Solar Probe and Solar Orbiter are designed to bring the question closer to direct measurement. Solar flares push this magnetic violence further. A flare occurs when magnetic energy stored in the solar atmosphere is suddenly released. Plasma is heated, particles are accelerated, and radiation erupts across the spectrum. X-rays and ultraviolet light surge outward. Charged particles can stream through interplanetary space. When solar activity reaches Earth, it can disturb radio communication, satellites, navigation systems, and power grids. It can also produce aurora, curtains of green and red light moving across polar skies. The corona and solar flares show that temperature can come from magnetism as well as fusion. The energy source is still the sun, but the immediate heating comes from fields rearranging themselves. Plasma follows magnetic lines, resists them, breaks them, and reconnects into new forms. The result is a kind of invisible machinery above the star's surface, where force lines store stress until they release it into heat and motion. Compared with later entries, the corona is not the ultimate furnace. It belongs early in the ranking because its temperatures are counted in millions rather than billions or trillions of degrees. Yet it is one of the most important hot environments for human civilization because it can reach across space and affect Earth directly. Its heat is remote in altitude and intimate in consequence. There is also a visual irony. The corona can be hotter than the surface while appearing faint because it is extremely thin. Temperature measures particle energy, not total brightness or density. A sparse plasma can be incredibly hot and still look dim. This distinction becomes essential as the list climbs into galaxy clusters, black hole environments, and cosmic shocks. The next step upward takes us from our own star to the hottest ordinary stars. Massive blue and blue-white stars can have surface temperatures far above the sun's, often tens of thousands of degrees, with the most extreme stellar surfaces reaching well beyond 40,000 degrees Celsius. Their light is harsh, rich in ultraviolet radiation, and powerful enough to sculpt entire nebulae. Around such stars, gas glows, dust erodes, and young stellar nurseries are carved into luminous pillars and cavities. These stars are massive, and mass changes everything. Greater mass means stronger gravity at the core, higher pressure, faster fusion, and more intense radiation. A blue star may shine thousands or even millions of times brighter than the sun, depending on its type and mass. That brilliance carries a price. Its life is short. While small red dwarfs may burn for trillions of years, the most massive stars may live only a few million years before exhausting their central fuel and moving toward collapse. Blue stars are among the universe's great engines of transformation. Their ultraviolet radiation ionizes surrounding hydrogen, creating glowing H2 regions visible across large distances. Their stellar winds blow bubbles into interstellar gas. Their radiation pressure pushes dust outward. They seed turbulence into the clouds that formed them. In a young star cluster, a few massive blue stars can dominate the environment, deciding which regions keep forming stars and which are stripped apart. Their surfaces, however, are still the exterior of the real furnace. Below the surface, their cores are much hotter than the sun's, and burn through nuclear fuel at a far greater rate. As they evolve, their interiors become layered with fusion shells. Hydrogen burning gives way to helium burning, then to carbon, neon, oxygen, and silicon in the most massive cases. Each stage requires a hotter core and lasts for a shorter span of time. The final burning stages may unfold in years, months, days, or even less, after millions of years of earlier life. The beauty of a blue star is therefore unstable. It is a brilliant announcement of future catastrophe. Its heat fills space, yet the deeper story is exhaustion. The star spends itself with speed, lighting nebulae and shaping galaxies while moving toward an ending that can become a supernova, a neutron star, or a black hole. In the ranking of hot places, blue stars occupy a dramatic middle ground, far hotter than the sun at the surface, still far below the temperatures reached when stars die. They also remind us that life around a star is not simply a matter of warmth. A planet close to a massive blue star would receive intense radiation, harsh ultraviolet light, and a short cosmic window before stellar death. The star may be magnificent from a distance, but its environment is violent. The hottest stars are often poor guardians for fragile worlds. Some massive stars enter a phase where their outer layers are stripped away and their inner heat is exposed more directly. Wolf-Rayet stars belong to this category. They are rare, luminous, and ferocious. with surface temperatures that can climb from tens of thousands to well over 100,000 degrees Kelvin in extreme cases. They lose mass through powerful stellar winds, sending material into space at thousands of kilometers per second. The star becomes a naked engine, bright and unstable, surrounded by gas it has torn from itself. Wolf-Rayet stars often represent a late stage in the lives of very massive stars. Their hydrogen envelopes have been removed by winds, binary interaction, or previous eruptions, exposing deeper layers enriched in helium, carbon, nitrogen, or oxygen. Their spectra show broad emission lines because their winds are dense and fast. The star is not simply shining into space, it is shedding itself into space. The heat of a Wolf-Rayet star has consequences beyond the star itself. Its radiation ionizes surrounding gas. Its wind carves bubbles and shells. Its lost material enriches the interstellar medium before the final explosion arrives. In some cases, Wolf-Rayet stars are considered possible progenitors of certain types of supernova and long gamma-ray bursts, especially when rotation and stripped envelopes allow the collapse to produce narrow relativistic jets. These stars are important in the ladder of cosmic heat because they reveal stellar interiors through violence. An ordinary star hides its deeper layers beneath cooler outer material. A Wolf-Rayet star has already lost much of that covering. It shines with a more direct view of nuclear history, showing material that has been processed in fusion and then expelled. It is a star in the act of becoming transparent to its own fate. The surrounding nebulae can look beautiful through telescopes, shaped like bubbles, rings, or turbulent clouds. Their beauty comes from loss. Each glowing filament is a record of mass leaving the star. Each shell is a sign that radiation and wind have done mechanical work on space. The star heats, strips, accelerates, and prepares the conditions for a final event. In a ranking of the hottest places, Wolf-Rayet stars stand above ordinary blue stars because their surfaces and winds can be far more extreme. Yet they still belong to the realm of stars that are alive. The next levels begin to cross into endings, where stellar heat stops being sustained equilibrium and becomes collapse, shock, and explosion. When a massive star reaches the end of its life, its core can collapse with extraordinary speed. The outer layers, no longer supported by the energy flow from within, are caught in catastrophe. The collapse and rebound drive a shock through the star. A supernova is born. For weeks or months, the explosion may shine with the power of an entire galaxy of stars, yet the visible brilliance is only part of the violence. Inside the event, temperatures can reach around 1 billion degrees Celsius or more. The physics of a supernova is a transition from stellar structure to cosmic debris. Before collapse, the star is layered with nuclear burning shells. Near the center, heavy elements have accumulated. When the core can no longer support itself, gravity takes control. Electrons and protons combine, neutrinos are produced in vast numbers, and a compact remnant begins to form. The outgoing shock, revived and shaped by neutrino heating and turbulent motion, tears through the star's layers and launches them into space. The heat of the shock changes matter. It drives explosive nucleosynthesis, creating and scattering elements. Some elements are forged in the star before the explosion. Others are made during the blast. The explosion sends carbon, oxygen, silicon, calcium, iron, and other elements into interstellar space. Future stars and planets form from clouds enriched by this material. A supernova is a furnace of destruction and distribution, carrying the products of stellar interiors into the wider galaxy. A supernova remnant remains hot long after the original flash fades. Expanding gas collides with surrounding interstellar material, producing X-ray emitting plasma at millions of degrees. Filaments glow in visible light. Shock fronts accelerate particles to cosmic ray energies. Magnetic fields are compressed and stretched. The remnant becomes a laboratory of high-energy astrophysics, preserving the memory of the explosion as a growing shell. The Crab Nebula is one famous example of such an aftermath. The supernova was observed on Earth in 1054, and today the remnant still glows, powered by a rapidly spinning neutron star at its center. The expanding nebula is a record of the star's death and the compact object it left behind. Other remnants, such as Cassiopeia A, reveal knots of heavy elements and X-ray structures that allow astronomers to reconstruct the explosion in detail. In this list, the supernova marks a major ascent. The sun's core reaches millions of degrees. Supernova interiors and shocks reach billions. Matter is no longer merely sustaining fusion. It is being torn apart, recombined, accelerated, and expelled. The event also carries a philosophical weight. Many ingredients of rocky planets and living bodies come from these explosions. Our calm existence is built partly from ancient stellar violence. The next hot environment is much larger than any star. Galaxy clusters are the largest gravitationally bound structures in the universe. They contain galaxies, dark matter, and enormous quantities of gas spread between the galaxies. This gas is extraordinarily thin, thinner than any vacuum most people can imagine, yet its particles move with tremendous energy. In major clusters, the intra-cluster medium can reach tens of millions of degrees. During violent cluster collisions, parts of it can reach around 100 million degrees or more. The Bullet cluster is one of the most famous examples. It is a collision between two galaxy clusters. The galaxies themselves mostly pass through each other because stars are separated by vast distances. The gas behaved differently. Gas from one cluster slammed into gas from the other, slowed down, heated, and formed a shock front visible in X-rays. Meanwhile, gravitational lensing showed that most of the mass remained offset from the gas, providing one of the strongest observational arguments for dark matter. This is heat made by gravity on the grandest bound scale. As clusters fall together, gravitational potential energy becomes motion. When gas streams collide, motion becomes temperature. The process unfolds across millions of light years and hundreds of millions of years. It is slow by human standards because the arena is immense. In terms of total energy, it is one of the most powerful types of collision in the universe. The intracluster gas is a strange furnace. It would not look like fire to human eyes. It shines mainly in X-rays, and because it is so sparse, it contains few particles in any given volume. Yet each particle carries immense energy. Temperature here measures the average kinetic energy of particles, while ordinary human intuition expects heat to come with density and brightness. A galaxy cluster teaches that a place can be extremely hot and still look almost empty. This environment is also important for cosmic history. Galaxy clusters grow through mergers. Their gas records collisions, turbulence, shockwaves, and energy injection from supermassive black holes at the centers of galaxies. X-ray observatories map this hot plasma to understand how large-scale structure forms. In the gas between galaxies, heat becomes a tracer of cosmic construction. In the ranking, cluster gas does not reach the highest temperatures, but it deserves its place because of scale. A supernova may be hotter in a localized region. A galaxy cluster stores heat across a volume so enormous that it challenges the imagination. It is a furnace without a flame, a weather system made of plasma, dark matter, and gravity. Black holes themselves do not glow in the usual way, but the matter falling toward them can become intensely hot. Gas approaching a black hole usually forms an accretion disk, a rotating structure of plasma. As material spirals inward, friction, turbulence, compression, and magnetic fields convert gravitational energy into radiation. Around stellar mass black holes, these disks can reach millions of degrees and emit X-rays. Around supermassive black holes, the disk can become bright enough to outshine the galaxy that contains it. Accretion is one of the most efficient ways the universe turns mass and gravity into light. Fusion converts a small fraction of mass into energy over long periods. Accretion onto a compact object can convert gravitational potential energy into radiation with extraordinary efficiency. The closer matter falls to the black hole, the more energy it can release before crossing the event horizon. The visible power of quasars and active galactic nuclei comes from this process. In the inner regions of an accretion disk, temperatures and particle energies can become extreme. The disk may glow in ultraviolet and X-rays. A corona of hot electrons above the disk can scatter photons to higher energies. Magnetic fields may launch jets. The system becomes a layered engine. Cold gas falling inward, disk plasma heating through friction, X-ray coronae flickering above the disk, and relativistic outflows carrying energy away. The environment around a feeding black hole is dynamic. Matter does not simply descend smoothly. It clumps, shocks, flares, and reconnects magnetically. Light from the inner disk is bent by gravity. Time itself is affected near the event horizon. Observations of black hole systems often show rapid variability, as if the disk were trembling under the strain of gravity and magnetism. The heat is not only high, it is unstable. Supermassive black holes and quasars can influence regions far beyond the disk. Radiation heats surrounding gas. Jets carve cavities into galaxy clusters. Winds from accretion disks can regulate star formation in host galaxies. A black hole may be compact, yet the energy released by falling matter can shape a galaxy's evolution. Heat becomes feedback, a mechanism by which the center of a galaxy speaks to its outer regions. This entry belongs above cluster gas and supernova remnants because accretion can drive plasma into regimes of tremendous radiation and particle energy. Still, the disk is only the beginning of the black hole's thermal violence. The next rung is reached when magnetic fields and rotation launch material into relativistic jets. Relativistic jets are among the most spectacular energy channels in the universe. They emerge from the regions around black holes and neutron stars, especially where accretion disks and magnetic fields interact. A jet can carry particles at speeds close to light. It can extend for thousands, hundreds of thousands, or even millions of light years. It can pierce through galaxies and inflate enormous lobes in intergalactic space. The precise launching mechanism is complex, but magnetic fields are central. Around a spinning black hole and its disk, magnetic field lines can become twisted and organized into polar channels. Energy is extracted from rotation and accretion, then carried outward in narrow beams. The matter inside the jet is sparse, fast, and highly energetic. In some regions, particles radiate through synchrotron emission as they spiral around magnetic fields. In others, shocks convert motion into heat and high-energy radiation. The temperature of a jet is not always a simple thermal temperature. Often, the particles are not in ordinary equilibrium. Astronomers may describe brightness temperatures or particle energies that reach enormous values, sometimes into billions or trillions of Kelvin in active galactic nuclei. These numbers need care, but they show that jets are among the most extreme particle environments known. They are places where heat, speed, magnetism, and relativity merge. Blazars are a special case where a jet points close to our line of sight. Because of relativistic beaming, their emission appears dramatically amplified. They can vary quickly and shine across the spectrum, from radio waves to gamma rays. A blazar is a cosmic lighthouse aimed almost directly at us, powered by a supermassive black hole and a disk of falling matter. Jets also heat their surroundings. In galaxy clusters, jets from central supermassive black holes inflate bubbles in hot gas. These bubbles rise, stir the medium, and deposit energy. This feedback can prevent gas from cooling too quickly and forming too many stars. A narrow jet launched near an event horizon can therefore regulate the thermal life of a structure millions of light years wide. The philosophical strangeness of jets lies in their directionality. Gravity pulls inward, yet the system produces beams outward. Matter falls, and energy escapes along the poles. The black hole is famous for capture, while its environment becomes one of the universe's most powerful engines of projection. In the ranking of hot places, jets stand as a reminder that the universe often turns collapse into emission. Gamma-ray bursts are brief, intense flashes of high-energy radiation. They are among the most luminous events known. Some last only fractions of a second, while others continue for minutes. Long gamma-ray bursts are linked to the deaths of massive stars. Short gamma-ray bursts are associated with mergers involving neutron stars. In both cases, compact objects, accretion, magnetic fields, and relativistic jets combine into one of the most violent displays in the cosmos. A gamma-ray burst is a focused catastrophe. The energy is often channeled into narrow jets moving close to the speed of light. If the jet points toward Earth, detectors register an intense flash of gamma rays followed by a fading afterglow in X-rays, visible light, infrared, and radio. The burst may come from billions of light years away, yet it can still be detected because the energy is concentrated and relativistically boosted. The temperatures and energies involved are extreme. The central engine may involve a newborn black hole or a rapidly spinning compact remnant surrounded by an accretion disk. Matter is heated, accelerated, and launched. Shocks form within the jet and where the jet strikes surrounding material. Radiation pours out at gamma-ray energies, the highest energy form of light. The event can briefly become one of the brightest beacons in the observable universe. Long gamma-ray bursts are often associated with massive stars whose cores collapse. If the star has lost its outer hydrogen envelope and rotates rapidly enough, a jet may drill outward through the star. When it escapes, it releases gamma rays into space. The supernova associated with such a collapse can be powerful, but the jet adds a directional component that makes the event visible across immense distances. Short gamma-ray bursts arise from compact mergers, especially neutron star mergers. When two neutron stars spiral together, they emit gravitational waves, collide, and can produce a black hole surrounded by hot debris. Jets may launch from the remnant, creating a short burst of gamma rays. The same event can produce a kilonova, where neutron-rich matter forms heavy elements through rapid nuclear reactions. Gamma-ray bursts deserve their high place because they compress enormous energy into brief time. They reveal how quickly the universe can move from stellar death or compact merger to radiation visible across cosmic history. Their heat is not a stable furnace. It is a detonation of physics, gravity, nuclear matter, magnetism, relativity, and radiation aligned for a few moments of astonishing violence. A neutron star is born when the core of a massive star collapses. In less than a second, a stellar core larger than Earth can be crushed into a sphere roughly the size of a city. The densities are extraordinary. Matter becomes packed so tightly that atoms are destroyed, electrons and protons combine, and neutrons dominate the interior. The newborn neutron star is one of the hottest compact objects in the universe. At birth, the internal temperature can reach hundreds of billions of Kelvin, and in some descriptions, the earliest core conditions approach around 1 trillion Kelvin. Most of the energy released during collapse escapes as neutrinos, nearly massless particles that barely interact with matter. A supernova may look brilliant in light, but neutrinos carry the vast majority of the gravitational energy. For a brief time, the newborn neutron star becomes a neutrino furnace. The surface cools rapidly compared with the object's long life, yet a young neutron star may remain hot enough to glow in X-rays for thousands of years. Deep inside, cooling is governed by neutrino emission, superfluidity, crust physics, and the uncertain behavior of dense nuclear matter. Astronomers study neutron star temperatures to learn about matter under pressures that cannot be produced in laboratories. Temperature in a neutron star is inseparable from density. In ordinary gas, particles fly through space and collide. In a neutron star, particles are crowded into quantum states. Degeneracy pressure, nuclear forces, and perhaps exotic phases of matter determine the structure. The object is hot, but heat alone does not support it. Quantum mechanics and gravity define its existence. A neutron star also has a surface gravity so intense that mountains may be only millimeters high. Light leaving the surface is bent. Time runs differently compared with distant observers. If the star rotates quickly, it can become a pulsar, sending beams of radiation into space like a cosmic metronome. If its magnetic field is extreme, it may become a magnetar, one of the next entries in this ranking. The newborn neutron star is a profound object because it is small enough to fit inside a city and extreme enough to test the limits of physics. It is the ember left after a massive star collapses, a compact remnant where heat, gravity, and nuclear density are forced into a single body. In the climb toward the hottest places, it marks the point where matter stops resembling anything familiar. Magnetars are neutron stars with magnetic fields of extraordinary strength. Their fields can reach 1,000 trillion times stronger than Earth's magnetic field. Such magnetism changes the behavior of matter, radiation, and vacuum itself near the star. The crust is strained by magnetic forces. The exterior magnetosphere stores energy. When the field rearranges or the crust fractures, the result can be a giant flare, one of the most intense magnetic events in the universe. A magnetar is already hot as a young neutron star, but its magnetic field provides an additional energy source. The decay of the field heats the crust and powers persistent X-ray emission. Sudden magnetic reconnection can release enormous energy in a fraction of a second. A giant flare can produce a brief spike of gamma rays so strong that it affects detectors across the solar system. The event is short, but the energy is staggering. The temperature during such flares can reach extreme values in the trapped plasma and fireball around the star. Radiation is confined by magnetic fields so powerful that they shape the movement of charged particles in ways impossible in ordinary environments. The flare may create a hot pair plasma of electrons and positrons. For a moment, the magnetar becomes a compact magnetic furnace, with energy stored not primarily in rotation or accretion, but in the structure of the magnetic field itself. Magnetars show another route to heat. The sun uses fusion. Galaxy clusters use gravity and collision. Black holes use accretion. Magnetars use magnetic stress on a scale so severe that the field becomes a reservoir of catastrophic energy. The star may appear quiet for long periods, then release a flare that reveals the violence stored around it. They also connect to broader cosmic mysteries. Some fast radio bursts may involve magnetars. These millisecond radio flashes can release enormous energy in a very short time, and magnetar activity is one leading explanation for at least some of them. In this way, the thermal and magnetic violence of a dead star may be linked to signals crossing galaxies. In the ranking, magnetars stand close to the top because they combine neutron star density with magnetic power. Their hottest regions are brief and compact, but the physics is extreme. They are among the universe's clearest examples of invisible force becoming radiation, heat, and cosmic signal. When two neutron stars orbit each other, they slowly lose energy through gravitational waves. Their orbit shrinks. The stars spiral closer. In the final moments, they whip around each other at tremendous speed, deforming under tidal forces, heating, cracking, and finally merging. The collision is one of the most extreme events in modern astrophysics. It can produce gravitational waves, gamma rays, heavy elements, a kilonova, and possibly a black hole. The temperatures reached in neutron star mergers can climb into the billions and tens of billions of degrees, with the densest regions entering regimes of nuclear matter under violent motion. The collision throws neutron-rich material into space. In that ejecta, rapid neutron capture creates heavy elements such as gold, platinum, and uranium. The glow that follows, the kilonova, is powered by the radioactive decay of freshly made nuclei. The event GW170817, detected in 2017, transformed this subject. Gravitational waves arrived first, followed by light from across the electromagnetic spectrum. For the first time, astronomers observed a neutron star merger through both ripples in space-time and radiation. It confirmed that such mergers are major sites of heavy element production and showed how compact object collisions connect gravity, nuclear physics, and cosmic chemistry. In a merger, heat is produced by compression, shocks, turbulence, nuclear reactions, and magnetic amplification. Matter is torn from the stars in tidal tails. Some material forms an accretion disk around the central remnant. Jets may launch if the conditions are right. The remnant may briefly be a hypermassive neutron star before collapsing into a black hole. Every stage is temporary, dense, and violent. The Kilonova light is less bright than a typical supernova in optical terms, but it carries a different meaning. It is the glow of heavy elements being born. A wedding ring, a platinum circuit, a trace of uranium in rock. Some portion of these materials may owe their existence to collisions of neutron stars. The hottest places in the universe do not only destroy form, they produce the rarest ingredients of planets. Neutron star mergers stand near the top because they combine extreme temperature with extreme density, gravitational waves, nuclear transformation, and element creation. They are short events, but their consequences last across cosmic history. A few seconds of merger can seed future worlds with matter that no ordinary star could easily make. The second hottest environment in this ranking can be created on Earth, though only for an almost unimaginably small fraction of a second. In heavy ion collisions, atomic nuclei such as lead or gold are accelerated to nearly the speed of light and smashed together. The energy density becomes so high that protons and neutrons melt into their constituents. Quarks and gluons, normally confined inside nuclear particles, enter a deconfined state known as quark-gluon plasma. This plasma can reach temperatures of trillions of degrees Kelvin. It is hotter than the core of the Sun by many orders of magnitude. Hotter than ordinary stellar interiors, hotter than most natural environments in the present-day universe. Yet it exists in a microscopic volume and vanishes almost instantly. Detectors do not observe it like a flame. They reconstruct its properties from the particles that stream outward after the collision. Quark-Gluon plasma is important because it resembles the state of the universe a few microseconds after the Big Bang. At that early time, the universe was too hot for protons and neutrons to exist as stable particles. Quarks and gluons moved in a dense, interacting medium. As the universe expanded and cooled, they became confined into hadrons, forming the building blocks of atomic nuclei. One of the surprising discoveries is that quark-gluon plasma behaves like an almost perfect liquid with extremely low viscosity. At temperatures where ordinary structure has been erased, matter can still flow collectively. This is one of the most beautiful results of modern high-energy physics. The hottest matter ever studied behaves with coherence. It is raw and ancient, yet not chaotic in the simple sense. The machines required to create it are themselves monuments to thermal contrast. Superconducting magnets must be kept extremely cold. Inside the detectors, collisions produce droplets at trillions of degrees. Extreme cold guides extreme heat. Human engineering becomes a narrow bridge between the quiet conditions of the laboratory and the first moments of cosmic history. This entry stands above almost every natural object in temperature. It is artificial in location, cosmic in meaning. For a fraction of time too short for ordinary imagination, matter on Earth returns to a state older than atoms, older than stars, older than light traveling freely through space. The hottest place we can meaningfully discuss is the early universe itself. At the beginning of cosmic history, heat was not confined to stars, disks, shocks, or compact remnants. The entire observable universe was hot, dense, and rapidly expanding. Temperature was everywhere. There was no outside space into which the fire could escape, no dark background against which it could shine, no stars to illuminate anything. The universe itself was the furnace. In its earliest fractions of a second, the temperature was far beyond anything now found in ordinary astrophysical objects. As time passed and space expanded, the universe cooled through stages. First came conditions where known physics approaches its limits. Later, quarks and gluons filled the cosmos in a dense plasma. Then protons and neutrons formed. A few minutes later, light nuclei appeared during Big Bang nucleosynthesis. Hundreds of thousands of years later, electrons joined nuclei to form neutral atoms, and light began to travel freely. That released radiation is now observed as the cosmic microwave background. The early universe is the summit of the heat ranking because it contains the origin of every later hot place. Stars are local furnaces that appeared much later. Supernova events are deaths of stars formed from cooled gas. Black hole accretion disks require galaxies, gas, and gravity shaped by earlier structure. Neutron stars require generations of stellar evolution. Quark-Gluon plasma in laboratories recreates a tiny fraction of what the universe once was everywhere. At the highest temperatures, matter loses every familiar form. Molecules cannot exist. Atoms cannot exist. Nuclei cannot survive. Protons and neutrons dissolve into quarks and gluons. Earlier still, the behavior of forces and fields may have been different from what we observe today. Temperature becomes a measure of how far reality is from the stable world of chemistry and solid matter. The cosmic microwave background is the cooled fossil of this history. Today it has a temperature of about 2.7 Kelvin, only a few degrees above absolute zero. It fills the universe as a faint afterglow, stretched by expansion from a time when the cosmos was hot and opaque. The coldest background in the sky is therefore a relic of ancient heat. The early universe also teaches that cooling is creative. As temperature fell, structure became possible. Particles bound together. Atoms formed. Gas gathered under gravity. Stars ignited. Galaxies grew, planets assembled, chemistry began. Life emerged in rare temperate zones around stable stars. The world we know is the result of a universe that began too hot for form, then cooled slowly enough for form to endure. The ranking of the hottest places leads from the familiar to the almost impossible. It begins with the sun's surface, a fire bright enough to define day on Earth. It moves inward to the solar core, where hydrogen becomes helium and mass becomes light. It rises through the corona, blue stars, Wolf-Rayet winds, supernova shocks, galaxy cluster collisions, black hole disks, relativistic jets, gamma-ray bursts, neutron stars, magnetars, neutron star mergers, quark-gluon plasma, and finally the early universe, where heat was not an event inside reality, but the condition of reality itself. Each level teaches a different form of violence. Fusion builds stars, magnetic fields heat plasma, gravity accelerates gas, shocks transform motion into temperature, collapse crushes matter into compact remnants, collisions forge heavy elements, particle accelerators briefly return matter to its primordial state. The early universe gathers all these themes into one origin, a beginning so hot that the structures we depend on had not yet become possible. There is a strange humility in this list. Human life exists in a narrow thermal shelter. Our bodies survive only within a small range of temperature. Our cities, histories, languages, and memories depend on moderation. Yet the matter that makes us was shaped by extremes. The carbon in cells, the oxygen in breath, the iron in blood, the calcium in bone, the gold in the ground, all belong to a story of stellar interiors, explosions, mergers, and cooling cosmic gas. The universe needed heat to make complexity, then needed cooling to preserve it. Too much heat erases structure. Too little energy leaves matter inert and dark. Between those limits, stars shine, planets form, oceans remain liquid, and minds arise to ask where the fire came from. The hottest places are therefore not distant curiosities. They are chapters in the ancestry of matter. When we look into the night sky, it seems cold and silent. That impression is real, but incomplete. Hidden inside the darkness are furnaces, shocks, flares, disks, jets, remnants, and compact stars where matter is pushed to its limits. The universe has cooled since its beginning, yet it continues to burn in scattered engines. Every point of light is a compromise between gravity and heat. Every atom is a survivor of temperature. The final answer to the hottest place in the universe is also the oldest answer. The universe itself was once the hottest place. Everything after that is a remnant, a repetition, a local return to the first condition. Fire came first, form came later. We live in the interval where the ancient heat has faded enough for meaning to appear.